before lunch we were talking about PES, photoelectron spectroscopy, and I'm going to pick this up. We use photoelectron spectroscopy to determine how much energy the electrons are held in the atom with. So as I had mentioned before lunch, it takes the PES device takes it uses light waves and determines how much energy it takes to remove all the electrons from a particular energy level. It says something down here in red. The highest energy, which is closest to the nucleus, like the 1s electrons, is farthest left. Now, that's not going to mean anything until you see the spectrum itself. So let's take a look at this. Now, once you get the hang of this, PES is very simple. So I'm not trying to teach you something that's all complicated. You're going to have to spend hours tonight trying to figure out. This for sure will be on the AP exam that you take on Tuesday next week, and it may wind up on the exam you take tomorrow as well. So the way a photoelectron spectrum looks is like this. It's got the spikes on it, and on the x-axis, now I didn't choose a very good one to start with because the x-axis is not labeled, but typically it would be called the x-axis ionization energy or binding energy. If we look at the next one quickly, it'll say ionization energy. One of the other ones I know says binding energy. So it said before, like in red up here, the highest energy electrons are on the left side. So I want you to notice the x-axis. It starts low over here far to the right, and then it goes up as it goes left. I don't quite know why that is, but it is that way. Always PES is like that. So every PES spectrum you see, it's going to start low and go up as we go this way. This is a logarithmic scale, as you see, the same distance is going up by powers of 10 rather than linear. That's not a big deal though. I mean, the actual values normally don't matter. What we need to remember is this. Farthest to the left are the electrons that are closest to the nucleus, and therefore they take the most energy to remove. So these would be the 1s electrons always. The farthest left are the closest to the nucleus. And then it goes 2s, 2p, second energy level, 3s, 3p. Now on the y-axis, what do we see here? It says relative number of electrons. This graph has grid lines on it. The next one, they don't always have the lines on it. So you just have to use your judgment, and your judgment will be right as to how high these peaks go. We all know that s orbitals and sublevels have room for 2 electrons, and then the p sublevel has room for 6 electrons. So the p spike should be 3 times higher than the s spike because there's 3 times more electrons in the p. So these are the 1s, these are the 2s and 2p, with the 2p being 3 times higher than that. And then 3s is the same size as the 1s and 2s, which means that it has 2 electrons in it. And then the 2p, or the 3p, sorry, on this one is not as tall as that 3p because the 3p is not full. It only goes up 4 lines, and it looks like every line, every grid line represents an electron. So this would end with 3p4. That's what sulfur's electron configuration looks like. This is the way that PES looks and what we do with it. So I'm just going to go through several with you. Now, you won't necessarily just get a spectrum and the question say, hey, what element is it? But a lot of times you do. Or it may ask you to analyze something about, like, why is this peak to the left compared to that peak? It'll have something to do with higher nucleus charge or something like that. But in this case, there's just the question, what element is this? I can tell from the font on this that this is an AP exam question as well. The x-axis, sorry, is ionization energy. And notice the unit megajoules per mole. I mean, it takes a lot of energy to remove electrons. So the farthest left, that would be the 1s electrons. Second cluster of them is 2s and 2p, the second energy level. And then it looks like the last electrons are in the third energy level over here. And I only see one peak that would have to be the 3s. Now that peak is the same height as the 2s and the 1s. So this must be 1s2, 2s2, 2p6, and then 3s2. That would be magnesium. That would be magnesium's photoelectron spectrum. So once in a while you get that, and then other times you'll get questions like this. No, this is a part of the webinar that they did in, as you see, March of 2014, where they were trying to teach us what PES looked like. So they had several sample questions on here, but some of the sample questions were just out there, and so I didn't want to include them. But yeah, here's another question: what element is it? We see the 1s are here, 1s2, 2s2, and then it looks like every 2 grid lines represents 1 electron. So there's an electron and there's an electron. So this 2s is 2 electrons. 2p, 1, 2, 3 electrons. That would be nitrogen. Now I had somebody in my first hour class, they looked at this quickly and they saw what it was asking for. And when they saw that last peak, they saw 3 electrons and they said, boron. If you look at boron, boron has 3 valence electrons, but they were just doing it too fast, and they just neglected the 2s electrons. So be aware of that. Be aware that you don't want to go too fast, because these are not difficult things. You don't want to get an easy thing wrong. So yeah, just be real careful with reading that, and I would on your mark 1s, 2s, 2p, like that, so you don't miss anything. Okay, I had found this on the free response of one of the questions in 2019. They were given this PES spectrum, and number 1, write the ground state electron configuration of this element. Okay, well, we have the 1s is farthest over to the left, and you can see that the energy is going up. It doesn't have it, doesn't say energy that way, but 0.9 times 10 to the negative 18, 4 times 10 to the negative 18, 7 times 10 to the negative 18. It's going up as we go left. So these are the 1s electrons, 2s, 2p. 2p, notice, is 3 times taller than 2s. There's 6 electrons in there. Then 3s2, 3p6, and then 4s2. So that would be the ground state electron configuration. It'd just be up to 4s2. That would be calcium. But then they asked, in part B of this thing, calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. Anybody in here in 11 AP English language? Are you really? Yeah. Look at all the prepositional phrases in there. Did you catch that? Yeah, your English teacher would not like that. And yeah, they obviously didn't run this by their AP English consultants. Yeah, from the valence shell of an atom of the element, 3 prepositional phrases in a row. Don't do that when you're writing. Anyway, yeah, so what they're asking for is, what is the wavelength needed to remove an electron from the valence shell? We have to know where the valence electrons are. That's these. Oops, I used the wrong marker there. These are the valence electrons. So we know the energy involved in removing those electrons, and therefore on the equation sheet it has E equals H times nu. So you can find the frequency of that light, and C equals lambda times nu. So if you know the frequency, you can find the wavelength. Or you can just combine these two, and if you remember doing this in chapter 7, energy equals H times C over lambda, and then we would just solve for the wavelength. And they actually made it easy for you. This is easier than like a test I would give, because if it was me giving the test, I would say give the wavelength in nanometers, because that normally is the unit that we use for wavelength. But that would mean converting to nanometers at the end. You don't even have to do that here. So this is a pretty simple calculation. -9th, yeah.
But we take our answer.
There's 10 to the 9th nanometers in a meter,
Yeah.
I should say. Yeah. Okay. Next one, this is my last one. This was the year before. I'm telling you, every year they put PES on there, so for sure you're going to see something like this on Tuesday next week. The complete PES of an element is represented by, very simple, looks like we have 1s2, 2s2, 2p3. Yes? Yeah. Yeah. Is that Marcus? This is pretty easy. So, don't be intimidated by this technique. It really, once you know what you're looking at, there's not much to it. Identify the element as nitrogen. But then, check this out what they did. This, I just think, that they're kind of ratty doing this. College Board is a very successful company, but I hope you don't work for them because I don't like their their lack of conscience. Back at that workshop that Mr. Hempel and I went to back in 2013 in the summer, they told us, hey, we're reworking this curriculum, and they gave us this new framework. They said we're removing things from the curriculum, we're adding some things in, adding in PES. Some of the things that they said they were removing was, number one, you don't have to memorize solubility rules anymore. But then the very next year, they put things that the students had to know whether they were soluble or not. They just had told us the summer before we didn't have to do that anymore. So they did that, and then they said, you don't have to do any more nuclear chemistry. We're taking nuclear chemistry out of it. We used to do a full chapter on nuclear chemistry. Talked about alpha decay and beta decay and half-life and all that. They said, you don't have to do that anymore. Then in 2018, they did this. And they do that, they do this a lot with nuclear decay. Now, I haven't said anything in this class about nuclear decay. But there you have it here. On this question, it says, a radioactive isotope of this element decays with a half-life of 10 minutes. And then they ask you questions about that, the kinetics of it. Calculate the value of the rate constant. Okay, now here's what I want you to know. I'm not trying to just give you these little facts to remember. You will remember this. Radioactive decay is always first order. And that's not that hard to remember. And I don't think you'll have any trouble remembering that. You know that first order dominates over all the other orders. Yeah?
Does the college board only test just like half-life for first order? Is that the reason they only give us the equation?
Yeah.
So it's always just first order?
Yes, yes. They only give you the half-life for first order. This is why. So the kinetics, we're just going to use the integrated rate law for first order and the half-life formula for first order. And then knowing that, it's very easy. But that they were, if they didn't want us worrying about nuclear decay, then they shouldn't put any nuclear decay on the exam. But they just do. Anyway, calculate the value of the rate constant. You know that T1 half, and it's on the equation sheet, equals ln of 2 over k for first order. So you can solve for the k, and that's what you have to do. It does say include units with your answer. Be very careful of this. You might be tempted to say, oh, the unit on first order is like 1 over time, 1 over second. But notice they gave you the half-life in minutes. So just be very careful. Really focus in on everything, and be clear thinking when you do this.
Yeah. Can we switch it to seconds?
No. Just leave it as minutes. And your unit will be 1 over minutes. If you change it to seconds, they won't mark you wrong if you use 1 over seconds. Then in part C, it says if 64 atoms of the radioactive isotope are originally present in a sample, what is the expected amount of time that will pass until only 1 atom of this isotope remains? Show how you arrived at your answer. Now in this case, you have a choice. There's 2 different ways you can do this. You can be scientific and say, oh, okay, since this is first order, we can use this. Natural log of A equals negative KT, which we know the K value, plus ln of A0. And we know that A0 was 64, and at the end, the A value is 1, and we know the K from this part, so you have everything there solved for time. You just want to set it. It says show you how you get there, so you need to show this. Or, if you understand what half-life is, and understand that for first order, half-life is the same. Every sequential half-life doesn't change, doesn't get longer or shorter. Knowing that it's first order, you can say, oh, okay, well, you start with 64, and then it goes down to 32, and that takes 10 minutes. Then it goes down to 16, and that takes 10 minutes. Then it goes down to 8, and that takes 10 minutes. Just keep doing that, and then add all your 10s together. It would be, I don't know how many steps, 7 steps, something like that.
60.
1, 2, 3, 4, 5, 6. It takes 60 minutes. That's all you have to do, and they would give you full credit for that. Because you're showing them that you know how to use the information and answer the question. You understand what half-life is? I didn't remember to tell my other class this, and we still have several days. But often they'll do this exam either in the main gym or the aux gym, oxygen is notoriously cold. Wear something that you can, like a hoodie or something like that, that you have something underneath it. Have something underneath it. But wear something that you can take off, a light jacket or something. I don't want you to be freezing cold when you're taking this thing. You're in there for a long time, and that can be really distracting if you're cold. I hate being cold. I keep light jackets in my cabinet over there. I never hesitate to grab one when the AC is kicked up too much, and just I don't feel like I can concentrate as well on it. So yeah, remember that. Yeah.
Are there breaks between like S?
Between the two parts, there are, yes. Yeah. But that free response is the second half, and you have an hour and 45 minutes, a long time. And I don't think they allow you to have snacks either, do they? You can't eat anything.
I don't even think you can have water.
Yeah, you're only allowed to keep the water next to you. Like, you're not allowed to.
You can't drink it. You can have it there, but you can't drink it. I didn't know that
Yeah,
either.
that's what he said.
I think I had mentioned to you also, maybe you've heard it, maybe you haven't. Two things, I guess. Number one, is everybody's iPad working fine? If you have any trouble at all with your iPad, like the keyboard's not working or whatever, go see Terrell, like pronto. He'll get you fixed up. If there's anything that's wacky about your iPad, get that taken care of. The other thing I was going to say is, the questions are going to be given to you through Blue Book on the iPad, but your answers are going to have a pencil that you write the answers on paper. So they call it a hybrid exam. Some of the AP exams are all computerized and digital, but this one is a hybrid where your answers go on paper. I think even the multiple choice, I'm not positive about the multiple choice, but I think that it's on paper as well. I hear that, and I'm not sure because I haven't seen this for myself, but somebody has said that if you need the periodic table, you have to click on it and open it, and you can't see either the question or the answers. Like it'll cover up either the question or the answer. You can move it around, but you're going to have something covered up when you look at the periodic table. And the equation sheet, same thing. You can open it up, you'll have to click on it, and then it opens it up and takes the screen, and you can't see the question again.
That's actually.
I wish they would have had some 10th and 11th graders consulting with them when they would have done this.
Grab one of these? Or is there nothing allowed?
I don't think you can have a paper in there with you. You can't take a paper in there with no way would they let you. And I don't know, because it could be, maybe those are available on there on the Blue Book app, but they actually may have in the answer booklet the periodic table and the equation sheet. I don't know. So I'm not getting too stirred up about it, but I definitely will gripe to them if you come back after the exam and tell me, yeah, sure enough, we couldn't see the question when we opened up the equation part. Because yeah, they need to do that better. Okay? Anybody else? Nishika, did you have a question? Okay, one other thing I wanted to talk about, we have about 10 minutes left. On packet number 1, of the review packet number 1, I believe this is question, if I'm right, question number 10. It looks like this. Can you find it? Avi, do you have it? Or can you get at it? Or somebody find it?
Number 10, yeah.
Is it number 10? Would you put that on there? I will let you have the TV. This is room 304. Would you put it on there? Yeah. The last thing I want to talk to you about is the process of chromatography. That's what this question is going to ask about if you've seen this before. Thank you. Can you write on this? It's okay if you can't.
Yeah.
Okay. So if you see the question, in the diagram below, a sample of ink, there's the ink right there, is placed into a column. The column has, it's filled with a substance, we typically call it resin, R-E-S-I-N. The resin here is, it's got a certain polarity to it. It's either polar or non-polar. It doesn't say which it is. It really doesn't say anything about it, except they call it the stationary phase. Stationary because it's not going to move. It's going to stay there while stuff moves through it. Chromatography always is going to have a stationary phase. You have several different options for chromatography. You can have column chromatography, where there's a resin that's in a column, a tube. The gravity is going to pull the something through. There's paper chromatography, where water is going to run up a strip of paper. It's kind of like paper towel, how water runs up it. There's other types of chromatography. There's thin layer chromatography and gas chromatography. There's lots of different ones. Chromatography is a pretty widely used technique in chemistry, and it's used to separate things based on their polarity. Now let me show you what I mean by that. It just says stationary phase packed in the column. So this thing has this resin. It's got a certain polarity to it. Then there's the solvent. The solvent is known as the mobile phase. So you've got something that's moving and something that's not moving. And this system is going to separate the components of this ink. We're going to assume, and Abby, I'm going to ask you to write, this next to the solvent, write polar. And then the stationary phase, let's make that nonpolar. Typically, this is the way chromatography is set up, where one of your phases is more polar than the other phase. There's a difference in the polarity of it. Now what happens is this. The ink is put in here, and this bulb is raised up, so gravity will pull the solvent down, and the solvent's going to flow through this resin stuff, and then you can see it's dripping out the bottom. Thank you. Remember, this is polar. If any of the components of the ink are polar, the solvent will carry them, will grab onto them. They're attracted to each other because polar attracts polar. Polar does not attract nonpolar. So the polar things will be attached onto the solvent and at least attracted to it, and the solvent will drag the polar things down the column with it. The things that are nonpolar, they'll just see the polar stuff coming through and it's like, oh, you're polar? I'm nonpolar. I don't really have anything to do with you, so I'm just going to stay here put. I'm more attracted to the nonpolar resin that's in here. So at the end of this thing, when the solvent has had a chance to run through, we'll see that the components of this ink have gotten separated. There's a separation of them. And the one that's the most polar will have traveled the farthest with the solvent. The one that's the least polar doesn't go with the solvent. It stays put. So when we look back up at the question, a sample of ink is in a column and a mobile phase is introduced, down it goes through there. Based on the data provided, which of these 4 layers has the greatest interactions with the stationary phase? In other words, which of the components of this is most attracted to the stationary phase that didn't move? Which one is it? The top one. The one that didn't move. The mobile phase was carrying the polar things with it because the mobile phase was polar. The non-polar stuff stayed there with the stationary. So that's what they're getting at.
So if you switched it and made the stationary polar, then the thing that's at the top would be most polar?
Yes. Yeah. So yeah, we could switch it. This could be a polar thing, that could be non-polar. So it's grabbing the non-polar things and separating. In that case, these would be flipped around. Yep. That's chromatography. It's very likely that you'll have a chromatography question. Guaranteed you're going to have PES, guaranteed. And likely that you'll have chromatography. Now, a lot of times the chromatography is paper chromatography. If I would have had one more day in the bonding chapter, we would have done a chromatography lab. It would have been paper chromatography. Paper chromatography is like this. You have a strip of paper. It's a thin strip of paper. And we'll put some mixture of colored things on it. Like what we used last year was Kool-Aid. We had some grape Kool-Aid and some cherry Kool-Aid. Mr. Hevel and I sat there back in the office. We drank Kool-Aid while everybody worked out here. No, I'm just kidding. I'm much of a Kool-Aid drinker. But what you do is you make a dot of this mixture of dyes. And we find the grape Kool-Aid actually has 3 different dyes in it. There's like red 40 and there's yellow, I think it's number 9 or whatever. There's these several different dyes. And cherry Kool-Aid, I think, has a couple of dyes in it too. So the chromatography is there to separate those two, the one that's more. So anyway, we put this into water, and the water runs up the paper. It's called capillary reaction when it defies gravity and runs up on the paper. It's so attracted to paper. So paper is the stationary phase. Water is the mobile phase in this case. And so the water being polar is going to grab onto the most polar, all the polar things are going to run up with the water, but the most polar things are going to travel the farthest along with the water. The moderately polar things will travel up, but they won't go as far as the more polar things. So you get this separation. If it was grape Kool-Aid, we get 3 dots, and the one that's highest up is the most polar. And the one, you can actually use this to identify unknowns in a mixture of things. So that's the way that chromatography works. It's a separation based on polarity. That's what I would want. If you're going to write anything down, chromatography is the process of separating things based on their polarity. And with that, my friends, I have taught you all that I can teach you. That was my last lecture. You will not listen to another lecture in the class. So we're done, and it's time to go. And if you have any questions, you can hang around for a few minutes, I guess. And so I was hoping I'd have, thanks for your help with that. I was hoping I would have a few more minutes left over so that you'd have a chance to ask questions. But I'll be here for a while after school today, and I'll be here in the morning, of course. If you have those difficult ones, you can't get
This curve, right? Yeah. Okay. So then, why do they bond when each other? Don't they want to bond with 6 and 3 as 2? So that
Energy wants to be minimized, right? Like you're running down a hill, right?
yeah.
So it's the farthest right.
Going